Good evening, everyone, and welcome to the Amateur Radio Technician class, session number 12. So during our previous session, we looked at our curriculum progress, the practice exams, digital modes, packet radio, APRS, PSK, DMR. We also discussed WSGTX, FT8, mesh networks. Then we talked about electrical safety, electrical wiring. Then we got into antenna and tower safety, as well as grounding and lightning protection, and the concept of duty cycle. And we ended with maximum exposure limits. And of course, we had our usual question pool review. All right, very good evening to you there, Adish. And hello, Mark. Great to have you guys. All right. So our agenda for this evening, we'll have a quick look at our curriculum progress. Again, we'll mention the practice exams. Then we'll get into the technical topics for this evening, which includes power supplies, voltage drop. We'll discuss digital mode interfacing. Then we go on to ferrite chokes, RF grounding, mobile power sources. Then we discuss microphone gain, what VFOs are, talk about keypads, memory channels, the feature known as scan, as well as what is squelch. We'll discuss repeater offsets, also digital voice hotspots. Then we'll go into some digital voice modes. Again, DMR, D-Star. Then we'll talk about bandwidth filters. Then we will also discuss the RIT, or RIT, and also known as the clarifier. Then we'll end with PTT, and then do our usual question pool review for all of the theory that we would have covered this evening. And of course, we will then announce the date for our next session. Okay. So on your screen, we have our curriculum and where we are. So as we see, we have made very good progress indeed. And we are on this topic station setup and operating controls, which we expect to start and also finish today. So pretty good progress. Just a reminder of the practice exams. These are the links. Never too early to do those practice exams. And of course, we take the opportunity to again congratulate all of the students who would have taken exams passed, and also those that would have received their US call signs, as well as their local Trinidad and Tobago call signs and call signs for various jurisdictions. We have participants from many places around the world, and congratulations in order to everyone who has been able to become licensed amateur radio operator. Okay. Just a reminder, we're using the No Nonsense Technician Class License Study Guide. Right. So let's begin again by having a look at what an amateur radio station comprises of, or a typical amateur radio station, or what one might look like. And we just use this slide to set the context for some of the theoretical constructs that we'll discuss. So we have our amateur radio station. We went through it previously. We plug our power supply into the wall. It could easily have been a battery. We power our transceiver. We have a microphone that we speak into. And maybe we have an antenna tuner that's connected via jumper cable. And from the antenna tuner, go outside to our antenna. Hopefully that's maybe on a very nice nifty tower like this. So this may be what an amateur radio HF station may look like, right? So let's discuss now the concept of voltage drop. So in the previous slide, we showed that there was a power supply that was plugged into a receptacle outlet and taking 120 volt AC or whatever supply you have in your territory and converting it to a voltage that the radio will use. And that is typically 13.8 volts DC. So we make the point that when we use a cable between our power supply and our radio, so this cable here, or DC power cable, we may call it. We need to make sure that we minimize the voltage drop across this piece of wiring that's connecting our power supply to our radio. The reason is that if 13.8 volts leaving the power supply, if we have a voltage drop that's too large, then we'll get less than 13.8 volts at the radio. So we want to make sure that we do a couple of things to ensure that we don't have any significant voltage drop. But what causes a voltage drop? You may recall that we talked about resistance in wire, talked about the concept of resistance. So resistance can cause a voltage drop. Ohm's law, if you remember correctly. So to mitigate against that, we may want to use a thicker gauge wire or heavy gauge wire that will ensure our voltage drop will be minimal. The other thing we want to do is make sure that the distance or the length of that wire is as short as practicable. So we don't want it to be too long, because the longer the wire is, the more the voltage drop is, the more the resistance would be, and that resistance will cause that voltage drop. So we shorten the wire to the minimum required, then that will assist. So that's the point that we make in this slide here. And it's an exam question, and it says to minimize the voltage drop when transmitting, short heavy gauge wires are used for transceivers DC power connection. So what they're trying to say here, when you key your radio, your transmitter, you press that push to talk and you start to transmit, maybe going out at 100 watts, you will experience a voltage drop if this cable, this wire, this DC power cable is not as good as it should be. So it needs to be heavy gauge wire, and it also needs to be as short as possible. So this is an exam question. All right. So again, we have our power supply and we have our radio, and they're connected via a DC power cable. So we may want to know, well, we have parameters, a power supply that is going to be adequate for use for our radio. So we need to know how much power we will require. And remember, we had a power formula, P is equal to IE. So we'll use this as a bit of a reference, not on the exam, but just to give us an idea of some calculations. We want to know if this is a 50-watt radio, what should this power supply be able to deliver in terms of current, the current rating? We already know that it's going to supply 13.8 volts. That's a typical DC voltage supply for almost any amateur radio, whether it's a VHF, UHF, HF, pretty much all of them, other than the ones that may already have a power supply built in that you can just plug into your receptacle outlet. It's typically 13.8 volts, so that's a given. And what we would need to know is, given it's 13.8 volts, what current rating or what amperage will we need for that power supply to be able to deliver? So to be successful when we not only receive, but when we transmit, because when we transmit, we draw a lot more power than when we receive, especially if we are using the highest power that the radio can transmit at. So if this is a 50-watt radio, and this is a 13.8 volt power supply, we can calculate what the current will be for a 50-watt radio at 13.8 volts. Now, if we do a straight calculation and using that power formula we had, if you remember, P is equal to I multiplied by E, and therefore if we do algebraic manipulation, or we use that little mouse plate that we had introduced maybe in session 2 or 3, we can get I is equal to P over E. So P will be the output power of this radio, and we're saying it's 50 watts. And V or E would be the voltage, which is 13.8. So if we were to do that division there, we put 50 on the numerator, 13.8 on the denominator, and we do a calculation, we'll get 3.62 amps. So we may say, okay, this power supply only needs to be 3.62 amps. Well, not quite. First of all, this radio is not 100% efficient, right? So we may have to put a lot more in to get 50 watts out, 50 watts of RF power, and then there's processing, there's heat losses, there's so many other things inside of there. But I just thought I'll show a calculation that if it were just 100% efficient, then we would only need maybe about a 4 amp power supply. But then you don't want to go exact as well. You need to have headroom, especially for surges and transients and those sorts of things, right? You can't go exact. So while we may be looking at a 4 amp power supply, we need to double it to maybe about 8 amps, right? Just for the efficiency. And then we need to add a bit of a headroom. So what we will say is that if this is a 50 watt radio, we need at least 12 amperes being able to be drawn from this power supply. And that's actually an exam question as well. They will tell you for a 13.8 volt power supply, and it's a 50 watt radio, what current must the power supply be able to deliver? And they'll give you a number of options, of which some of them will be too small, some of them will be too, well, I guess way too large, I guess, and some will be just about right. So the exam, it's 12 amperes is the correct answer. So we just did a little calculation here to show you it needs to be at least this, but why this will not work, because it's not 100% efficient, right? So this was just a reference calculation, not in the exam, and also just to show that we do use these formulae from time to time to put a finger in the wind and get an idea, you know, so this is how we do it. But the exam question talks about a 13.8 volt power supply, which is this here, and it's a 50 watt mobile FM transceiver, which is this here. What will be the amperage or the current that the power supply must be able to deliver for this radio to operate at the 50 watt rating? And it will be 12 amperes. So 13.8 volts and 12 amperes is an appropriate power supply rating for a typical 50 watt output mobile FM transceiver. This is an exam question. All right, so this is a slide you've seen at least twice before, and this is just to set the stage for the ongoing discussion over the next couple of slides, which is we're going back into digital modes. And if you recall, when we talked about a digital mode, and it occurs to you, yes, digital mode, that means we're connecting a computer to your radio, you'll be quite correct. So this is just showing anytime we talk digital modes, generally, at least digital data modes, it's a computer connecting to a radio or transceiver, sometimes directly and sometimes via an intermediary device, depending on the age of this radio. It may require an interface, sometimes called a terminal node controller, TNC. All right, so just reminding us all, digital modes, computer connected to a radio to send a signal off into the air. All right. So when we communicate with digital modes, we have to interface our computer, whether it's a desktop computer or laptop, running some operating system, maybe Windows, maybe Linux, maybe Mac OS. And then we have our radio or transceiver. And this is an HF transceiver here. And there are signals when we interface the radio to the computer that we need to know about. And there are three specific signals that go between these two, whether it's a USB cable or some interface. The idea that there are at least three signals that we need to be concerned with. And of course, there are ports on the computer that represent the connection for each of these signals. So we need to know about these signals. One of them is what we'll call the receive audio. And that's the audio that goes from the radio to the computer. So even though it's the computer talking and listening, it is still audio at the end of the day. The radio will receive a signal via the antenna, come through the feed line or the transmission line into the radio. The radio will demodulate and send audio out to the computer. If we were using voice mode as opposed to digital modes, then we'll be listening to the person via the speaker. But this is digital modes where we have interfaced our radio or transceiver to a computer. So this audio out of the radio goes to the line in or microphone in of the computer. So the computer can listen to those tones that's coming back from the radio and making sense of them, decoding them on our screen. But of course, the same way it will receive a signal and we are ready to transmit now. So we received a message, someone is calling us and we have to reply now. Our radio will transmit based on the signal that our computer will send to it. It has to do that over a signal line, and that is called the transmit audio. So there's a line, whether it's via USB or whether it's actually a hard physical line, that goes into a jack. But the point is there's a signal that goes in the opposite direction, which is the transmit audio. It goes from the computer to the radio, and then the radio processes it, puts the audio signal onto the carrier wave, and it sends it out as radio frequency to the antenna, and that goes into the air to be received by another amateur radio operator. That's what we're trying to achieve when we're using digital modes. So we have these interface signals, one that goes from the radio to the computer with the audio bringing it in, another one that sends the audio, the tones that are generated by the computer. Remember, in digital modes, we are not really talking or using voice or phone mode. Our computer is doing the talking, so it has to send that audio via a signal cable or some port onto the radio, right? And of course, in addition to the audio going from the radio to the computer and from the computer to the radio, we need something to tell the radio to transmit, and that may be a PTT or transmitter keying circuit or signal. So those three signals are typical. They may be achieved in different ways, but these are the three signals or signal types that we need to be aware of when we're using a digital mode with our computer connected to or interfaced with our radio. Whether we have an intermediary device or not, these signals still need to get there. So in some cases, we may just be able to plug a USB cable between the laptop or computer and the radio. And in some cases, we may have something of an interface device. Sometimes it's called a terminal node controller or some other name, that signal link USB, or any of those other commercial, or you can, as a ham radio operator, build your own interface, but you need to know that these are the signals. And that's an exam question. So the signals used in a computer radio interface for digital mode operation are receive audio, that's this first one, transmit audio, that's the other one, and the last one, transmitter keying, sometimes called PTT or push to talk, right? So those are the three signals that we need to be aware of for the exam. All right. So this is, one second, let's go back. Right. So we're now coming to a specific digital mode that we're going to use to communicate with another amateur radio operator. So we're using a digital mode and we are using FT8. We dealt with FT8 previously, and we also dealt with using WSJTX software to operate FT8 mode. So this is a software that's running on the computer, running on top of the operating system. We have interfaced our computer to the radio successfully. These are these three signal lines that we have going on there. And the computer software will listen to the signal that's coming from the radio into the computer and decode it on screen. And the computer, when we are ready to transmit and send the signal, will send an audio signal. It will be a digital signal, but it will be audio nonetheless, that is going to the radio, and then the radio will need to transmit. That's where this other signal comes in, the transmitter keying or the push to talk signal, where the computer will say, transmit on this signal, and it will transmit. But what will it transmit? It will transmit the audio that the computer is sending to it onto the carrier wave and send it off into the air via radio frequency, right? That electromagnetic wave that leaves the antenna. So for the exam, we need to know that the transceiver audio input and output connected in a station configured to operate using FT8, that's the mode, is connected to the audio input and output of a computer running WSJTX software. So let's dissect what this is saying here. It said what we just said. The transceiver, that's this, our radio transceiver or HF transceiver or radio, audio input and output, right? So this is the audio input and this is the audio output from our transceiver or radio. And we are configured to use FT8. So we're operating FT8. So it's FT8 that we are operating here to the audio input and output of a computer. So that's the audio input and audio output of the computer here, of a computer running WSJTX software. And there's our trusty WSJTX software on the screen. At least try to make it look as though it's running that, right? So that's what we have dissected this point to make. And so this is an exam question. We need to know about these signals, and we need to know that it's the audio input and output that allows the FT8 mode and the WSJTX software to communicate from the computer to the radio. All right, again, sticking very similarly, again, similar diagram that we have on your screen. This is another exam question, so let's just read it out. So the computer line in to transceiver speaker connector is the connection made between a computer and a transceiver to use computer software when operating digital modes. So this is just another way of saying the same thing that we just said, right? So we have a digital mode that's operating, It could be using WSGTX software. It could be using FT8, FT4, JT65, one of those digital modes. It could be PSK31. Doesn't matter, but it's a digital mode that we are using. And the computer line in, that's the line in on the computer here, to the transceiver speaker connector. So this is our transceiver or radio transceiver or UHF radio. The speaker connector, that's this line leading to that port on the radio, is made between a computer, which is this here, and a transceiver, which is our radio, to use the computer software, which is the software that's running here, when operating digital modes. So you see, they're just making it sound a little bit complicated, but we understand it's a digital mode, therefore a computer using software via cable of some sort or interface to the radio, and we are listening or we are receiving signals, and it's decoding on our computer, and we are sending signals that someone else will decode on their end. Digital mode. All right, let's move on to a different topic. All right, so of course, as amateur radio operators, it's not all that every time we are operating, things will be hunky-dory, smooth operation. We may have problems, we may experience interference, and we, as hams, would need to know how do we sort out interference. So we need to be familiar with a component that's known as a ferrite choke. And we'll discuss this later on in the course, and when we come to the general, we go to town on what ferrite chokes are. But for now, on your screen, this is what the form factor may look like, a cylindrical disc like this, right, made out of a material known as ferrite. It may also be this sort of clamp on, and you may have seen these on power cables. You may have a plug that you plug into the outlet that goes to some computer device, and you may see these bulky little things around it. That's a ferrite choke, and it's used to help with interference. So this is what ferrite chokes look like. And we may want to use them in our amateur radio station with our connections. So a connection that is from our power supply to our radio, that's the DC power cable, we may want to put a ferrite choke around it. Also, if we have a microphone that is connected to our radio and there's a microphone cable, we may also wish to put a ferrite choke around that cable as well and probably wrap a few turns. So ferrite choke is one of those things that we can use to help eliminate some of the interference or distortion that we may experience in people telling us that we're sounding distorted when we're transmitting. So we may wish to use these ferrite chokes that will help with the RF that's generated on our station that's feeding back into these lines. The lines basically, they're shielded, yes, but they may still act as an antenna and pick up those signals and other signals from around and cause distortion and interference in our system, right? So this is what the ferrite choke looks like, and it can help when we use them correctly to reduce electromagnetic interference. And that's an exam question. Ferrite chokes can be used to cure distorted audio caused by RF current on the shield of a microphone cable. So we did say our microphone may have a cable going to the radio, and if we strip apart the cable, we'll see the outer part is a braid, so that's the shield, and then you have the actual signal wires itself. But RF, maybe from our antenna or some other signal source in the shack or home, may impinge on this microphone cable. So this microphone cable here, we just have a little strip away version of it here, so you can see what the wires look like inside the microphone cable. And this picks up that stray RF or radio frequency signal and will induce a current on it, and that may cause the audio to sound distorted when we are transmitting. So if you're getting that and another ham is telling you you're sounding as though you're a bit distorted, and you look at your station and say, all right, let me try some ferrite chokes. You clip them on, clamp them on, or put them in line with the cable, wrap them around the ferrite choke. That could solve your problem. So this is an exam question. Let's move on. All right, grounding and bonding. So we dealt with that before, but we are looking at it now from the perspective of RF. So we were talking about electrical grounding and bonding for surges and short circuits, as well as lightning protection and so on. But we are also considered from a radio frequency perspective. We need to ground our equipment for RF also. So the same ground that we're using, but the point that is made here, ideally we should use flat straps as that conductor that we connect our power supply, our antenna tuner, our transceiver, and if we have other meters in line, let's say go into our transmission line or jumper cables, if you have other instruments inside of there or other devices, maybe an amplifier, you need to use one of these copper braid straps and connect it to your grounding bar on your station, and that grounding bar is further connected to your ground rod. So this is an exam question. Flat copper strap conductor is preferred for bonding at RF, and RF is radio frequency. So not only electrically in the sense, but also for radio frequency. It reduces, keeps your shack protected, so you won't be hot in the sense of RF, and also avoids those dangers associated with RF in your station itself. Right? So make sure you ground all pieces of equipment to that common ground bar. This is the exam question that you will get. All right, so we're now going to talk about mobile sources. Where do we get power if we install? So this is our radio installed in a vehicle. We're putting it inside of our car. And then we have our feed line, transmission line that goes to the antenna on maybe on the roof of the car. But then we have to power it somehow. So we have our DC power cable. So the red wire will go to the positive terminal of the battery. The black wire, which is the negative, you may think, well, we should connect it to the negative of the battery, but that's not actually what we do. We connect it to the chassis ground, a very solid part of the vehicle. Once you have a negative grounded chassis, which is most cases, you connect that negative wire to the sturdy chassis ground as opposed to onto your battery. And that's an exam question. The negative power return of a mobile transceiver in a vehicle should be connected at the 12-volt battery chassis ground. So we'll call it 12 volts, we'll say power supply requirement is 13.8 volts, but we could equate 12 volts and 13.8 volts for our purposes to be about the same, right? For now anyway. So let's dissect this point. The negative power return of a mobile transceiver. Negative power return is the negative power cable, the black line, black cable, black conductor. In a vehicle, that means you're connecting it inside of a car of some sort, should be connected at the 12-volt battery chassis ground, not to the battery itself, but to the chassis ground, wherever that exists on your vehicle. This is an exam question. All right, so we have another exam question that we need to understand. If we are connecting to a battery, how long will that battery last us? So we don't need to learn the calculation for the exam, but we have put a calculation here. So let's go through the calculation and then we'll come to the point about for the exam. So if this is our battery in our vehicle, let's, again, to keep the numbers simple, let's imagine this battery is rated at 100 ampere hour. Right, so it may be 75, it may be some other figure, but let's say this is a 100 ampere hour battery. That's the battery installed in your vehicle. And let us say that this transceiver, when you are operating it, draws 2 amperes. So we wouldn't talk about whether we're receiving or transmitting. Let's just say it draws 2 amperes. The question will be, if this is a 100 ampere hour battery and this radio transceiver draws 2 amperes of current, how long will this battery last? So you can calculate it, and we're saying that the operating time that we'll get is the ampere hour rating of the battery, which is 100 ampere hours, divided by the average current draw, and we're saying for this radio it's 2 amperes. So we, on the numerator, put 100 because it's 100 ampere hours, and on the denominator we put 2 amperes, and we divide and we'll get 50 hours. So if this battery is a 100 ampere hour battery, and this radio on average draws 2 amps of current, this battery should last about 50 hours, more or less. So that's a kind of decent calculation to make to give you an idea of how long. So of course, if it were a 200 ampere hour battery, if it were a 20 ampere hour battery, if it were, let's say, a 19 ampere hour battery, you can do the same calculation as to how long your battery is going to last before it needs to be charged or before it dies or it becomes unusable for you. All right, so let's get to the exam question in relation to this bit of theory here. So you can determine the length of time that equipment can be powered from a battery by dividing the battery ampere hour ratings by the average current draw of the equipment, which is what we just did in a formula. Right? So how long will the battery last? You find out what the ampere hour rating of the battery is, and you divide that by the current draw or the current consumption, or how much current does this radio use, or the current usage, current draw, all different things, right? All right, let's do a couple more slides before we take our break. All right, so of course we are amateur radio operators and we have our radio transceivers. We expected to know how to use it, and there are features on our radio that we need to know about so that we sound good and we are able to receive the other amateur radio operator who is transmitting. We must be able to listen to them, and hopefully they'll sound loud and clear, and hopefully when we are transmitting, we are also going to sound loud and clear. So if this is our microphone and it's connected to our radio or transceiver, and the transceiver of course is connected to our antenna, and we're going to transmit, so we press or push to talk on the microphone and we speak into the microphone, and the other operator tells us we are sounding distorted. One of the suspects is that maybe our microphone gain setting, so just imagine this were a knob called microphone gain, right? It may be set too high. I may need to back it down a little bit or reduce it, because if it's too high, or I'm speaking too close to the microphone, or I'm speaking too loudly into the microphone and the gain is high, then I may overmodulate. And therefore, when I do that overmodulation, remember when we speak, we introduce our voice onto the carrier wave and then it goes out onto the air. But if we overmodulate, which is such a thing, our audio may sound distorted. So on the left-hand side here, we have some little graphs showing, okay, if we do 50% or half modulation, this is what our signal will be leaving our antenna will look like. If we do 100% modulation, notice the difference. This is 100% modulation. This is what our signal will look like. But if we do 150% modulation, we're actually going to sound distorted. Note how the signal goes in these areas here, where it should have been flat like this. Right, so this is overmodulating and it's distorting our signal. So just to give you an idea, why too much of a good thing is good for nothing, right? So we don't want to be beyond 100% modulation, right? And one of the settings, or one of the knobs, or one of the internal menu settings in a radio will be the microphone gain. Sometimes that gain could be on the microphone, it could be a knob on the radio. Hypothetically, it could be a digital setting. You have to go through the menu system and set it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. But that's a setting, microphone gain. If it's too high, you will overmodulate. You will drive your audio too hard into the radio and it will sound distorted, and you might even cause a bit of interference in the process. You may use more bandwidth than you should be using for the mode. So this is an exam question. It says the effect of excessive microphone gain when you're using a single sideband transmission is distorted transmitted audio. So know that if it's an exam question, another operator say you're sounding distorted, well, back off the gain. All right. So now it sounds like a good time, I think, to take a 2-minute break, and then we'll come back and cover the rest of our slides. So let's get up, take a little stretch, maybe drink some water, have a bathroom break, and we'll see you back in about 2 minutes time. All right. So, Vishon, the exam that we would have mentioned that's coming up likely in August will be in person, face to face, and it will be held at the Telecoms Authority located in Barrett area. Right. So further information on that will be forthcoming over the next couple of weeks. So there is going to be an in-person meeting, right? In-person exam, I should say. All right. So let's pick up where we left off. Right. Okay, so welcome back, everyone. And just to say, sometimes we have radio stations. If you're a fan of FM radio, in Trinidad and Tobago, we have quite a few FM radio stations, and some of them are very clean, sound very clear. However, there are some that are not properly adjusted and sound very distorted. And the more that you become discerning, you'll realize just how horrible some of them sound. They're overdriven, and they think that they're sounding great. Same things with happens with party booths and so on. Drive, and it's so distorted, and sometimes people think loud is good, but it's loud and distorted. So as amateur radio operators, we strive for good quality audio so that we can be loud and clear. Right. Okay, so let's continue. So another feature of a radio is the tune-in dial. So if we look at a radio here, there's usually a tune-in dial. So that's not the only way that you could tune the frequency or punch a frequency in, the frequency that you're going to listen to or transmit on. You have a dial, and sometimes it's called tuning dial. It's sometimes called the VFO, for variable frequency oscillator. So it's called the VFO. Quite often you'll hear it called that by hams, but this is essentially the tuning dial. Now, if I'm going to be speaking to another amateur radio operator and the frequency is 146.820, and I'll challenge participants, tell me what meter band that is, right? So we'll give the answer in a little bit. All right, so we're on this band, we're on some band, and the frequency chosen 146.820 megahertz. That's the frequency that I'm going to be speaking with to another amateur radio operator. But if instead of punching in or dialing in 146.820, I inadvertently go to 146.825, right? So 5 kilohertz off. The thing is, I may still hear the person may still hear me, but I'm actually going to be off frequency, and I will sound distorted to that person, and they will also sound distorted to me because I'm off frequency. I'm a little above or below the frequency. And of course, on this band, and hopefully someone has figured out what that band is, 146.820, what band is that? So if you said it's the 2 meter band, you'll be quite correct. So I'm on the 2 meter band, and I'm on a frequency, but I'm not on the correct frequency because maybe I punched it in incorrectly or I touched the dial. That's why sometimes there's a lock button that allows us to lock. So even if we were to touch the dial, it wouldn't change the frequency. But I touched it and it went up by 5 kilohertz or went down by 5 kilohertz, and I'm still hearing the person. But the effect is they will sound distorted. So that's actually an exam question. It says that the result of tuning an FM receiver above or below a signal's frequency is distortion of the signal's audio. So if we're just off frequency, the person will sound distorted or we will sound distorted. That's an exam question, right? All right. So a couple more features of a radio. So this is a 2 meter transceiver. Right? It operates in the 2 meter band, and that's the frequency display that we have here. There's also channel memory as well, and so there's a number here showing what channel it's on, similar to television or similar to anything else, cable that has a channel, so it's channelized, but the channel is actually translating into a frequency, right? So remember, we have been talking about frequency and wavelength. That's why that trusty table that we have is very important for us to pay attention to, because we are using radio frequency. But sometimes it's convenient to save that frequency into a channel. So we go to channel 8 or go to channel 2. Instead of every time we have to punch in 146.820 or even remember what it was. Was it 820? Was it 850? Was it 860? Was it 825? So, I can punch the frequency in and save it to a channel. That's a feature of many radios. Radios may have a keypad as well, like this. So it's a microphone, but it also has a keypad with digits. And of course, there are buttons and knobs on the radio itself. And of course, we talked about the tune-in dial, called the VFO, where we could change frequency as we turn it left or right. It will go up and down in frequency. Or if we're in channel mode, we'll go up and down in the channel, right? So we need to know for the exam, if this frequency I want to operate on is 146.820, there are two ways I can get to that frequency. I can use my tune-in dial, also known as the VFO, variable frequency oscillator. That's what VFO means. I can use this is my tune-in dial, and I could go to the frequency. So if I want to go to 146.930, I just turn this until this says 930. Another way I can do that is I have what they call a DTMF keypad here. I can just punch in the number on the keypad. So I can say 146.930, enter. So those are two ways I can change my operating frequency, via the VFO knob or via the keypad. And that's actually an exam question. It says the keypad or VFO knob can be used to enter a transceiver's operating frequency. This is our transceiver. This is the operating frequency on the display that we are using. And this is our VFO knob. And this is our keypad on our radio. Also, as we mentioned before, if you have frequencies that you are custom using, maybe the call channel, maybe repeater frequencies or frequencies that you as an amateur radio operator like to use, it's part of the band plan and you can legitimately use it. You have a license for that and you select the frequency and you want to use it over and over again. Maybe you want to save it into a memory channel. So that's a quick way to get access to the frequency instead of each time having to remember the actual frequency and then keying it in all the time or turning the dial and taking time. Literally in seconds, you can go to channel 1, channel 2, or just change the channel. And that's an exam question as well. A way to enable quick access to a favorite frequency or channel on your transceiver is to store it in a memory channel. And that's just showing some of the features of the radio, channelized memory. Of course, there's another feature. If we have many channels or you have a band of frequencies and you want to, go through those frequencies and listen on it, instead of being on one frequency only, you want to see if there's activity on any of those other channels, you can use a feature on the radio that's called scan. So sometimes it can be a button that is assigned to scan. It could be a button on your microphone as well at the top or on the side or on the keypad itself, or maybe in one of the soft keys on the radio itself. You press the scan button and it will round robin and go through and cycle through all of the frequencies. If it's channelized, it'll go channel 1, channel 2, channel 3, channel 4, channel 5. And if you only have 5 channels, it'll start back at channel 1, channel 2, channel 3. The radio will automatically change the channel, spend maybe a second or so on it and just go through quickly. And once there's a transmission on one of them, it will stop and you'll hear that transmission. So that's called the scan feature. It goes through all of the channels that you have programmed or a frequency range so that you can monitor for activity. And that's another exam question. The scanning function of an FM transceiver tunes through a range of frequencies to check for activity. So that's a scan feature or the scan button. Right, yet another feature of a radio is the squelch, right? Interesting name. And on this radio here, this is the squelch knob, right? Sometimes some radios may not have a knob for squelch, but it may be a setting in a menu item, but quite often ham transceivers may have a squelch. Handheld radios sometimes don't have it. It's a setting in the menu, but mobile radios, base radios like these, quite often they do have squelch. But you may be asking yourself, well, what is squelch? What does that do? So if you have ever tuned on your broadcast FM dial and you go to a radio station, you'll hear the music, you'll hear the talk show host talking and so on. But if you were to change frequency, you just go up a little bit into a space where there's no transmission, you will hear sort of hash sound, like just noise, white noise sometimes it's called, right? Just hash. And you turn the volume up and you'll just hear this hashy noise continuously. Well, on amateur radio, that's the same noise we will hear if we go to an unoccupied frequency. There's no transmission, no signal, no legitimate signal. You just hear that loud kind of noise, right? So what that squelch does, it causes the noise to disappear by just turning the squelch button just until the noise disappears. And any signal that goes above the noise, you will hear it. If a signal is with the noise, you may not hear it. So you need to be aware of that. As a matter of fact, that's a technique that hams can use as well. There's a weak signal and you're not hearing it and you know that it's there. Someone has told you or you're expecting it, you can back the squelch off to 0 and you will hear the hash and the noise, but you may actually hear that person who is with the noise floor. They are sounding very weak, but you might actually be able to hear them by backing off the squelch. So that's what squelch does. It shuts off that background noise by just reducing the signal sufficiently so that you don't have to hear that all the time in your head. So it's a good feature to have, and it's also a good feature to be able to back it off if you're trying to listen to a weak signal. And those are exam questions. The purpose of a squelch function is to mute the receiver audio when a signal is not present, because you don't want to hear that hash continuously like that, right? That's very disturbing. Also, the squelch is adjusted so that weak FM signals can be heard by setting the squelch threshold so that the receiver output audio is on all the time. What that simply means, if we dissect this, is you turn it off to 0. You turn the squelch to nothing so that the audio is on all the time. You'll hear the hash continuously, but if the weak signal comes in, you might actually hear that person by having backed off that squelch. So as amateur radio operators, we know how to be discerning about the use of that feature called squelch. All right, so we need to know about repeater offset. So we have dealt with repeaters before, but we'll delve a little more into the repeater. What is a repeater? If you remember, we said a repeater, again, similar to cell towers. They tend to be on a tower or maybe on a hill somewhere that's high up. And we'll have our radio, our handheld radio. It could be mobile and even base, but we have our handheld radio. And we want to talk to someone else that's on the other side of the terrain. Maybe this is a hill or another city. And this radio is not able to do simplex. So at the bottom here, we have the case for simplex. If we were within line of sight, we can go direct one radio to our radio. But if we do not have that coverage, we want to use a repeater. So we will transmit the repeater on a high spot, will hear our signal, and it will retransmit or rebroadcast our signal wide area, and everyone else will hear us. But for that to happen, you need to have two frequencies. You have the uplink frequency and you have the downlink frequency. So the repeater essentially extends the range capability that you would otherwise not have. Again, similar to cell phones and cell towers, except that for cell towers, there are literally hundreds of towers all over the place. For us in amateur radio, we may have several amateur radio repeaters as well, but typically we are usually using one repeater up on a hill somewhere on a tall building. And that's repeater operation. Okay, so what we need to know about that is that the two frequencies, the uplink frequency and the downlink frequency in amateur radio is typically separated by 600 kilohertz. So whatever the uplink frequency is, it's usually minus 600 kilohertz or plus 600 kilohertz to get to the other one. So that is a fixed, usually a fixed relationship between the transmit and receive frequencies for a repeater. So your radio will be transmitting on one frequency and receiving on another when you're using a repeater. And that's because simultaneous operation. While you are transmitting to the repeater is simultaneously transmitting back to every other radio. But that wouldn't be possible if it was trying to do it on the same frequency, right? So it has to be another frequency it's transmitting on. So that's why a repeater operation requires two frequencies, an uplink and a downlink for that simultaneous transmission. And there's a relationship between the two frequencies, which is for 2 meters, or for VHF, it is 600 kilohertz, either plus or minus. But specifically, we call that the repeater offset. And in our radio, and for amateur radio on the 2 meter band, it's typically 600. And if you were to go into your radio, you will actually see that as a typical offset, 600 kilohertz, right, or 0.6 megahertz. So that's the difference between the repeater transmit and the repeater receive, or your radio's transmit and your radio's receive. So remember, in the repeater operation, your radio is transmitting on one frequency, the uplink frequency or the go frequency, and then it's coming back down on another frequency to all the others and yourself as well, right? So that frequency separation is 600 kilohertz, and it's called the repeater offset. So if you were to subtract 600 kilohertz from 147.930, you'll get 147.330. That's 600 minus this, right? So it's called the offset frequency. So you're just programming this frequency, and the offset will allow, when you transmit, to transmit 600 kilohertz below. So that's the importance of offset. You just program in the frequency of the repeater that you want, and you enable the offset, and it's typically 600. So offset is an important setting on your transceiver. So there's an exam question, and it's the difference between a repeater's transmit and receive frequencies is known as the repeater offset. Exam question. Not on the exam here, but we say for the 2-meter band, the offset is typically 600 kilohertz or 0.6 megahertz. Okay. All right, so we come back now to digital and digital voice. So previously, we would have said that in addition to digital modes where you have your computer that is talking to the radio for you and sending out the signal via the airwaves, instead of you using your voice or phone mode, we also mentioned there's another construct or concept of digital in amateur, and that is digital voice, as opposed to analog voice. So that is where our voice is encoded digitally onto the radio signal and then transmitted, right? So it's a little block diagram to give you a little idea of how it might work, not on the exam, but extra information for those who may want to know how it actually works. You can take a look at that diagram on your own time. And essentially, our voice is digitized and goes and imposed on that carrier wave and goes out over the air. And that encoding takes place. And on the opposite side, when our signal is received by the receiver, the other amateur radio operator, that person's radio now will receive it and decode the digital signal and convert it back into the voice. So that is digital voice. And there are many advantages of digital voice. You can consider it improved audio quality. You can consider there may be less background noise. And there's also the possibility, because it's digitalized or digital, it can also use the internet as a means of transport. You can send your signal not only via RF, via radio frequency. You can also, and we'll come to it in a little bit, using repeaters and hotspots, they can now take that digital signal and put it over the internet quite easily because it's already digitized. All right, just for extra information as well, there are several digital voice modes. We're going to deal with 2 of them, but there are others as well. So there's DMR. We talked about DMRs already. Remember, we said that uses TDMA, very efficient use of spectrum, 12.5 kilohertz. Previous class, we talked about it. DMR. And also there's D-Star, Digital Smart Technology for Amateur Radio. So we'll be talking a little bit about D-Star, but there are also others such as C4FM, sometimes called System Fusion. People may refer to it as YSF or YSX and so on, but it's really C4FM. And P25, which is another mode. Some of these are commercial modes that amateur radio operators use, but they're all digital voice modes. And encoding your audio into a digital format and sending it over the air, as opposed to just keeping it in analog mode. So digital voice modes. Right, so we did mention that there is something called hotspots, right, and repeaters. So we need to know what a hotspot is for the exam. So on your right-hand side here, we have a handheld transceiver, this radio here. It's a portable, very portable device, handheld, right? Or sometimes called a walkie-talkie. And this particular radio is a digital radio. So it will do analog, yes, but it also has the capability of encoding your voice onto a digital voice mode. And this radio happens to be a DMR radio, right? So this radio here will encode your voice, encode my voice, and then send it over the air via the antenna. Now, if we had another radio nearby, the person will hear us and they will be able to decode us, as long as it has also that same digital voice mode and it has the similar parameters. So that's radio to radio, simplex operation. But we can also use our radio and connect it to a hotspot. And this hotspot is a radio hotspot. It will operate on the same frequency as this radio, but it will also be internet connected either via hardwire, or some of the hotspots can also connect to the internet via wireless, right, meaning Wi-Fi. And what that will do is it allows us to expand our capability beyond just the local nearby amateur radio operator, or if we were to use a repeater locally as well. We are again limited geographically to the maximum coverage of those repeaters. But with the hotspots now, we can extend global coverage, because via the internet, this is internet connected, or radio signal, let's say DMR will go to this hotspot via the antenna, and will put this signal onto one of the networks, the digital networks that exist outside there. And we can talk to people all around the world via various talk groups, or rooms, as we may call them. So this is a possibility using a hotspot. And we have a slide coming up that shows the different types of hotspots. But essentially, you can do radio-to-radio communication, simplex operation. You could do radio-to-repeater, as we have seen. But we could also do radio-to-hotspot, our own personal little, almost kind of repeater in our household. Doesn't have a very wide area coverage. I mean, you usually just want to use it around the house. So that's why it's itty-bitty antenna. But this is the hotspot. And we'll see some other form factors as to what hotspots look like. And there's an exam question associated with it, which is the function performed with a transceiver, this here, and a digital mode hotspot, which is this, is communication using digital voice or data systems via the internet. So it just simply means we are speaking into the radio, analog to digital converters, our vocoder is converting it into digital voice, and it's going to the hotspot, and the hotspot now is converting it and carrying it over IP or over the internet, either wirelessly or via an Ethernet cable onto the internet. And of course, all around the world, there are other networks as well that will pull our transmission and send it elsewhere around the world to other people who may also have hotspots, and even to repeaters that are internet connected as well. So this is an exam question that you need to learn, function of a hotspot. So here are some examples of what hotspots look like, right? So on the left here, we have what's sometimes called an MMDVM jumbo spot. Very popular, probably one of the more popular ones that are outside there. This is the antenna that will receive and also transmit digital voice. You have a nice little OLED display here, shows you the DMR mode, shows you the talk group, which we'll come to in a little bit, some other LED signals. Of course, this USB is powering it, right? So, and there's a little mini Raspberry Pi 0 on inside of there, by the way. And of course, you have what you call a Pi hat, which is a radio transceiver that will receive and transmit. So this is how our hotspot is constructed internally. But we have other form factors. One that we saw on the slide before, one of the early versions of the Shark RF Open Spot. Very cool, nice, easy to use hotspot. I believe this one is called a Rugged Spot. Again, this has a Raspberry Pi. It has a Pi hat and an OLED display with an antenna. So again, we are taking our walkie-talkie, transmitting digital voice into it, and it's putting it onto the internet on one of the DMR networks. You see the DMR logo here as well. Another version of the Open Spot, one of the newer versions as well, has Wi-Fi enabled as well. Also a battery inside of there, so it can self-power. And this is what is called a dongle. That could create a hotspot, a USB dongle that you can put into a computer or Raspberry Pi or something. It has the antenna as well for RF, and this will put you onto those digital voice network, whether it's the DMR networks, the C4FM networks, the P25, NXD, and any of those other digital voice networks. It creates a hotspot situation for you. So again, not in the exam, but just to make it real, to show you what hotspots might look like. And hams may want to invest, configure. Of course, it's running on operating system. You have to go to the web page for the device and configure it for your frequency, your talk group, your DMR ID, and so many other parameters that you have to set it up for. But these are what hotspots look like. So we come back to DMR. We talked about DMR before. And what we need to learn about DMR, we had this bit of information previously. So this is just a refresher. It uses TDME. Right? So DMR is very efficient. And we need to know for DMR that there's something called a talk group. So if I'm communicating with my handheld repeater, my handheld to a repeater, there are talk groups on this repeater. So it's not to say I'm limited to one channel of operation. I can be talking on this repeater here, but I may be on a talk group, and persons who are in the same talk group will hear each other. So unless you go into what is called promiscuous mode, you will not hear someone else in another talk group. So people in different talk groups that are talking will only hear each other, or the membership within the talk group. And that's actually a configuration on your radio, the talk group, various talk groups that you may have. So you may have talk groups for different purposes, right? But the idea is that persons normally on the same talk group will be able to hear each other, and others in other talk groups will not be able to hear them, right? So that's the point of this exam question. A talk group on a digital repeater is a way for groups of users to share a channel at different times without hearing other users on the channel, right? So if you're in a talk group and someone else is in another talk group and they're talking amongst their talk group, you will not hear them, right? So exam question, talk groups. Some people think of talk groups as channels. In a way, if you could think about it like that, I suppose, to understand it. But strictly speaking, it's not quite. It's a talk group. Okay. All right, sticking with DMR. So there are a couple other exam questions that we need to learn. So let's just go through them quickly. So we talked about the talk group that you may want to join to be able to speak to other hams on that same talk group. And the way to join that talk group is you have to program your radio with the talk group's ID or code. So if it is talk group 374, which on DMR is Trinidad and Tobago's talk group, you have to program on your radio using software like this. You could certainly do it on the keypad perhaps, but it's a lot easier to program your radio using software like this. So you'll have to punch in the frequency and the talk group and all the other settings that you need to put inside of the radio to make it work. So for the exam, you need to know to join a talk group on DMR, you have to program your radio with the ID of the talk group, or the code as it's called. And you'll learn in a little while that this programming is called the code plug, which is the next exam question. A DMR code plug contains the access information for repeaters and talk groups. So all a code plug is this is the software or similar software that you might use to program your radio for the DMR mode. You have to put the frequency, you have to put, what the talk group is, and so many other bits of information, color code, time slot, and all of that. But when you save that and you download it, depending on who you are, you may say it's uploading or downloading, depending on your perspective. When you're uploading that configuration to the radio, that configuration is considered the code plug. Right? So you need to be familiar with that term. A code plug contains the access information for repeaters and talk groups. So all of this information that you're programming in is the code plug. Also, another exam question, a specific group of stations that is selected on a digital voice transceiver by entering the group's identification code. So if you want to select a particular group, it's the group identification code, which is the same as the talk group ID. So again, similar to point number one, they just state it a little bit differently, but you need to learn that for the exam. And last exam question, if you look here, I don't know if you can see it, this is not the greatest of I do apologize, it's not as clear, but if you can see it, it says color code and there's one, right? So color code is one of those settings for a talk group. And for you to talk to someone else on a talk group, you need to be using the same color code. So if you're on one, the other person that you're talking to, the color code setting on their radio must also be one. Because if it's mismatched, you will not be able to communicate, right? So by default, color code 1 is used. So the purpose of the color code used on DMR repeater systems is that it must match the repeater color code for access. So again, 1 is the default. It's usually what is selected, but just bear in mind, if you put 2 in there and you're trying to transmit, you're trying to receive, it's not going to work. You need to match the color code. All right. So let's now come to another digital voice mode. We mentioned that we'll be talking about it just a little bit. It's called D-Star. And on your screen, we have some settings in a D-Star radio that you have to set. And one of the most important settings is your call sign. So as amateur radio operators, we mentioned that you'll get a call sign. My amateur radio call sign is 9Y4R or 9 Yankee 4 Romeo using phonetics. So if I'm programming my D-Star radio with my call sign, that's what I have to put into the call sign memory location. So I have to go into the menu and punch it in. I must put that in so that the mode will work, right? Also, other digital voice modes as well, DMR, you have to put your call sign in or your ID number and all these things, right? So that's an exam question. Your call sign must be programmed into a D-Star digital transceiver before transmitting. So let's dissect this. Your call sign, that's your amateur radio call sign. That's what you get when you sit the exam and you apply for a license. When you get a license, you get a call sign that you're authorized to use. And you must punch that in or program that into the transceiver before you transmit, because actually when you transmit, that call sign is going digitally. Even without you saying it, it's going to accompany your transmission because it's a digital mode. That information accompanies. And when you speak, your voice is also going along with your call sign digitally. So this is an exam question. All right, before we go through the next couple of slides, just to pull back up a representation of the amateur radio station, let's not lose sight of what we're trying to achieve here. We have our power supply that's plugged in. It could have easily been a battery. We have our radio transceiver. We have a jumper cable that may go to our antenna tuner. And then our antenna tuner, using a feed line or transmission line, goes to our tower that has our HF antenna on. So this is what we are talking about, just to bring us back as to why we are doing all of these theoretical constructs and understanding how to operate. It's because this is what we are trying to utilize. All right, so again, another feature of the radio called filters or bandwidth filters. On your right hand side here, this is an LCD screen, and you will see these notch filters represented like this. And what we need to understand or learn is that our radio, especially those with digital signal processors, and even the older radios that use the physical components, can process the signal if we're getting a lot of interference to notch out the interference and have us focusing only on the signal that we want to get. So that's the purpose of filters. So we can selectively focus in on the signal we want and reject the signal that we don't want. So we may be on a frequency here, and just close to the frequency we're listening to, we are getting some noise. So what we could use is a narrower filter that may reject some of the extraneous information. It might be a tone, or it might be a hiss, it might be some sort of other signal that's impacting on us listening or receiving a signal. We can filter that out by using maybe a narrower filter that will help us in being able to listen to what we want to listen to. The radio operator that is speaking, who you're trying to listen to, using a filter might help. So we have a couple of exam questions that we need to learn. They say that the advantage of having multiple receive bandwidth choices on a multi-mode transceiver is that it permits noise or interference reduction by selecting a bandwidth matching the mode. So let's dissect that. They're saying there's an advantage of having multiple receive bandwidth choices. So what that simply means is that we can select a menu of these notch filters inside of there. There's several of them, so it's an advantage. And the reason is that it allows us to reduce the interference by selecting the appropriate filter for the mode that we're using. If we're using Morse code or CW, if you're using SSB or single sideband, there we can use a narrower filter and get rid of the extraneous information that we don't need, so we could focus in on. So that's what this bullet point is. But also we need to learn that if we are using single sideband or SSB, the filter setting that we would optimally use for SSB is the one that's set to 2400 Hertz or 2.4 kilohertz. So 2400 Hertz is the receiver filter bandwidth that provides the best signal to noise ratio for SSB reception. We need to learn that for the exam, 2400. So just to sort of do a little compare and contrast, you know, the filters. So we showed what it will look like on a radio. So you have a narrow filter, that's a 500 Hertz filter, and we may use this for Morse code. This filter here is 2400 Hertz, and it's very good for single sideband, so notice a little wider. And then we have a wide filter here, right? So just a little bit of a comparison, a visual comparison to show that the filter here is a little narrower than this one, is a little narrower than this one. So just a little visual to show the filters that's available on the radio. And it's really the bandwidth, 500 hertz, 2400 hertz, and you can have, of course, other settings in between. Right. All right, just a couple more slides before we go into our question pool. So another feature on a radio is called the RIT, or the clarifier. But before we get into that feature, let's talk about calling CQ. You'll hear amateur radio operators say, call CQ, or someone is calling CQ. When you hear that term, it just simply means that an amateur radio operator is going to call someone. And when they do that, they may say CQ, 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 right? So that's why they will say that. Or if they're listening to someone making a call, that other person that they're listening to may be calling CQ. So anytime you hear ham radio operators say, they're going to call CQ, that just means that they're going to call someone, or they want to engage in a conversation, or have what we call a QSO, as we may say, right? So anytime you hear CQ call, it just means that two hams want to talk to each other, right? Okay, so let's talk about the feature on the radio that we need to know about for the exam. So there's a feature called the RIT, Receiver Incremental Tuning. That's the RIT. It is also called the clarifier. Now, what that does is that sometimes, when you're listening to a radio operator talking, they may sound a little bit, the pitch of their voice might be a little too high, or it might be a little too low, it might be a little too bassy, it might be a little too high pitch, a little bit too whiny. So you might want to adjust the pitch, and you can do so without affecting your particular transmission and all of that. You could do it also by changing the frequency, but you really don't want to do that. So you use the RIT, or the clarifier, to just turn a little bit, and you can adjust the pitch of that incoming audio. So that's actually a technique that hams will use to listen to the received signal a little bit better. They just turn that RIT or clarifier a little bit to the left or a little bit to the right until the radio operator sounds nice and clear. So that's an exam question. The RIT or the clarifier control could be used if the voice pitch of a single sideband or SSB signal returning your CQ call seems to be high or low. So you go on the air, you call CQ, and someone responds to you. They sound a little bit off frequency, a little bit high pitched, a little bit too bassy. As they talk, you turn this clarifier until they start to sound good. All right. Last slide before we go into our question pool. So there's another feature of our radio, and that's our microphone. And to use our microphone, we have to press the push to talk switch on the microphone. Sometimes that could be on the radio, could be a foot switch, but there's something called the PTT, or stands for push to talk. So this microphone on your screen here has this little bar called PTT, and I can press this. And when I press this, this engages my transceiver and says, hey, I'm transmitting, or I want to transmit. And I just simply speak into the microphone, and that will modulate the carrier wave, and then I'll be able to be heard by another amateur radio operator. Right. So when we press this push to talk, what that does is actually grounds a signal wire, and that is what enables the radio to go from receive mode to transmit mode. And on the right hand side here, we'll have a little bit of a block diagram, not exactly a schematic, but just a bit of a block diagram that shows that when we press the push to talk, we go from receiving to transmitting. And that's the effect of this push to talk, or press to talk, or button to key, whatever you may wish to call it. Even if it's a handheld microphone, you still have that button. It's called the push to talk, or the PTT. And we have an exam question in relation to this. The function of a transceiver's PTT input is to switch the transceiver from receive to transmit when grounded. And that's just how the circuitry operates. When you press this, it grounds it off and it starts to transmit. And of course, it throws off the receiver or switches off the receiver section while you're transmitting. And this is an exam question. So this other slide that we have is, we'll be repeating this just to have it near hand. Persons may like to refer to this from time to time. Remember, we threw a little question out to you guys a little earlier. We said, okay, it was 146.820. What frequency band is that? And of course, if we consulted our trusty table, we'll see that was the 2 meter band. Right, so a good table to have around. So let's now go into our question pool. All right. So we are on page 73 of the PDF is page 76, but the actual page in the book is page 73. So let's go again. All of these questions, we have dealt with the theory in this evening's session, so we will essentially speed through them. First question in question pool: why are short heavy gauge wires used for a transceiver's DC power connection? Well, we said it is to minimize the voltage drop when transmitting, right? So use heavy gauge wires and make sure that they are nice and as short as possible. Next question: which of the following is an appropriate power supply rating for a typical 50 watt output mobile FM transceiver? So you'll see why we did a little working there, right? So first of all, it has to be 13.8 volts. The answer must contain 13.8 volts, not 24 volts or not anything else. But then the two options that we have is 4 amperes and 12 amperes. Now, when we actually did the calculation, remember we came up with 3.62, but remember we also said that the radio is not going to be 100% efficient, and then we should not have a power supply that is exactly rated for what we need to use. We need to have some headroom. So it cannot be 12, it cannot be 4 amps, right? So the answer is 12 amps, right? So for that 50 watt transceiver, 13.8 volts at 12 amps. That's the power supply rating minimum. Okay, next question. What signals are used in a computer radio interface for digital mode operation? So that's that little diagram where we show the 3 signals. It's the receive audio, the transmit audio, and the PTT or the transmitter keying. Next question: how are the transceiver audio input and output connected in a station configured to operate using FT8? So FT8, dissecting that question, is a digital mode. So therefore we have a computer connected to the transceiver. So the answer is to the audio input and output of a computer using WSJTX software. And that's what you need to use to do FT8 mode. And it needs to be interfaced. That's where you get the audio input and output. Remember, the computer is listening to the tones and decoding it, and also crafting those tones to transmit via the radio. Next up, which of the following connections is made between a computer and a transceiver to use computer software when operating digital modes? Okay, so it's the computer line in to transceiver speaker connector. So that's the connection. Next up, which of the following could you use to cure distorted audio caused by radio frequency current on the shield of a microphone cable? So we introduce you to the ferrite choke. That's what you do. Wrap it around the cable or use the cable and wrap it inside of the ferrite. Good solution. Works quite often. Which of the following conductors is preferred for bonding at RF? So we said flat copper strap is what we should prefer. Next question in the question pool. Where should the negative power return of a mobile transceiver be connected in a vehicle? So let's dissect this. So we're talking about a vehicle or car. And they're asking us negative power return. In other words, the black cable. Where should we connect that inside of the vehicle? So we said it's at the 12 volt battery chassis ground. Okay. Go again. How can you determine the length of time that equipment can be powered from a battery? So that's basically asking us, you connect your radio equipment to the battery and you're using it. How long will the battery last? Well, we get two things. We get the ampere hour rating of the battery and we get the current draw of the equipment. And we therefore divide the battery ampere hour rating by the average current draw of the equipment. Next question. What is the effect of excessive microphone gain on SSB transmission? So we said if we have too much gain, our audio will sound distorted. So the answer is distorted transmitted audio. Don't drive it too hard. Okay. What is the result of tuning an FM transceiver above or below the signal's frequency? So we said, if we do that, we may still be heard and we may still hear the other person, but there might be distortion of the signal's audio. Next question. Which of the following can be used to enter a transceiver's operating frequency? We said there are two ways. We can use the keypad to punch it in, or the VFO knob and dial it in. Okay, next question in the question pool. All right. What is a way to enable quick access to a favorite frequency or channel on your transceiver? So we did say that we can store it in a memory channel, save it. What does the scanning function of an FM transceiver do? It tunes through a range of frequencies to check for activity. So that's the scan feature. What is the purpose of a squelch function, right? So that's that strange word, funny looking word, squelch. It is to mute the receiver audio when a signal is not present. Keep the place quiet instead of having to listen to that hash all the time. Next question. How is squelch adjusted so that a weak FM signal can be heard? So imagine you have that squelch adjusted, so you have no noise, but there's someone coming in, their signal is in the noise floor. So it's below what the squelch is silencing. So what you do is you turn the squelch off. So set the squelch threshold so that the receiver output audio is on all the time. In other words, back the squelch off. Yeah, what is meant by repeater offset? So we said that was the difference between a repeater's transmit and receive frequencies. You remember that for 2 meters, it's 600 kilohertz. Okay. Next up, what function is performed with a transceiver and a digital mode hotspot? So we showed that radio and handheld radio on the hotspot. It's used for communicating using digital voice or data systems via the internet. That's what we use the hotspot for. Connect to the internet. All right. What is a talk group on a digital repeater? It is a way for a group of users to share a channel at different times without hearing each other on the channel or hearing other users on the channel. Next question about talk groups. How can you join a digital repeaters talk group? In other words, how can you join a talk group? Well, you simply have to program your radio with that talk group ID. Okay, next question. What does DMR code plug contain? Well, remember we said that that really is a configuration, and that's what code plug means. Well, it contains the access information for the repeaters and the talk groups. In other words, the programming. How is a specific group of stations selected on a digital voice transceiver? Again, same thing. We enter the group's identification code, also known as the talk group number or talk group ID. Next question. What is the purpose of the color code used on DMR repeater systems? Yes, that's one of the settings, the color code. So it must match the repeater color code for access. If it doesn't match, you will have no access. You will be transmitting, the repeater will ignore you. Which of the following must be programmed into a D-star digital transceiver before transmitting? Well, you must enter your call sign into the radio. Okay. Next question. What is the advantage of having multiple receive bandwidth choices on a multimode transceiver? So we said that we can, of course, use the various bandwidth filters accordingly, because it permits noise or interference reduction by selecting a bandwidth that matches the mode. Okay, next up. Which of the following receiver filter bandwidth provides the best signal to noise ratio for SSB? We said 2400 Hertz. Please learn that for the exam. Single sideband, that's the best filter or notch filter, 2400 Hertz. Right, for CW, it's 500. But for SSB, it's 2400. Okay. Which of the following controls could be used if the voice pitch of a single sideband signal returning your CQ call seems too high or low. So let's dissect that. So we are calling CQ. We want someone to answer us. We call CQ, give our call sign, and listen for someone to reply to us. We don't know who we are calling. We're just saying, hey, we want to speak to someone. So we're calling CQ. Of course, when we hear that person return, they may sound a little bit high pitch or low pitch or bassy. So while they're talking, we tune their voice by using the RIT or the clarifier. All right. So last question in the question pool for this evening. What is the function of a transceiver's PTT input? So that's the push to talk input. It switches the transceiver from receive to transmit when it's grounded. So that's how it operates. So we have a couple questions I see here. Let's see if we can deal with them quickly. So Vishwan, if you can't make that exam session, well, two ways. You can either do the remote proctored online exams, or you can wait for the next edition, which may happen several months after, right? So try and make it if you can, but there's also always the option for remote online, or what we call remotely proctored exams. Jillian, yes, so all of these documents that we use are sent via email. There's a link that contains all of the documents, right? So everything is shared. The books, the text, the slide deck, all of the documents are shared with all participants. We try to do it as quickly as possible, usually within a day or two of the session. All right. So let's go back to our slide deck a moment. Right. Okay. So, right. So, Vishwan, the exam, it hasn't been confirmed the date as yet, but the volunteer examiners are looking to time an exam for when we have completed this course. So we are estimating somewhere around mid-August, right? So not yet confirmed, and we will be announcing it here a couple of weeks in advance, right? So you could pencil that in, middle of August for the exam. And of course, last session, we will be providing a lot more information about the exam. Session number 1, by the way, also has quite a bit of information about the exam. So we encourage participants, if you missed that, have a look at session 1 to answer many of your questions. But of course, last session, we will also be talking about it. Okay. So let's, of course, please send an email if I've missed any of your questions, or send me a WhatsApp. Reminding students, we'll encourage you to take a look at this particular video. It's 1.5 hours long. It's stuff that we won't cover in the course itself, but very useful for operators, radio operators, new radio operators, even persons who have been around for a while. Encourage you to take a look at it, some practical radio operating tips. Our next session is next week, Friday, 7th of July, 2023, usual start time, 8:30 p.m. So folks, thank you very much. Be safe out there. I think we have a yellow alert for TNT, tropical wave incoming. So please be safe. Have a good night, everyone. Take good care.